Any opinions on the midterm? Eh?
It was kind of good. I could do some of that, not all of them, but yeah, it felt good.
That sounds quite ideal, right? I mean, as students, you would expect everything to be easy, especially when the undergrads, when I teach them, they expect exam to be totally easy. What they seem to ignore then is that, well, that doesn't help anyone's grades, right? So an exam can be quite hard, exam can be quite easy. It doesn't have much to do with your grades. It all depends on whether you tried your effort. And the ideal exam is one such where some problems felt like they are easily doable, some problems felt like you had to work hard to get it, and maybe one problem where you had no idea what's going on. I don't think there was any problem like that in this exam, but that might
Mhm.
change person to person. So I have not graded it yet. I will be grading it this week and then getting back the solutions to you. The second homework is released. One of you protested to me that it has things which I have not covered. That's not really true. Virial equation of state is something is taught in PCAM. So if you have done the the prerequisites to this class, you should be knowing what it is. You should be able to try it. And regardless, everything will be covered today anyway, and it's due next Thursday. After this, we will be having one more homework, maybe two, but most likely one.
Mhm.
Any questions? The attendance has slowly, I mean, all of a sudden, or maybe slowly dipped. So I need to go and get hold of people who are not attending and try to understand why is it they're not attending. Maybe I should give some pop quizzes or something. Okay, so just to remind you what we were doing, we were talking about this magical quantity called G of R. It's not actually that magical, but it's quite useful and it can be measured from scattering experiments and things like that. And before talking about G of R, we talked about a bunch of things such as the probability of observing a specific particle at R1 and a specific particle at R2, and the probability of observing any two particles at R1 and R2 and things like that, right? So we did all this and we talked about one useful property of GFR. We showed that if we average minus d by d of R1, the full potential U of the n particle system with respect to the position of the first particle, this is the average force experienced by the first particle, keeping R1, R2 fixed, and the bracket, the average here means averaging over everything else. And then Nathan asked last time, what about the momentum? So remember, momentum we have completely ignored in the very beginning. We just said kinetic energy is separate. We are not going to talk about it. This turned out to be equal to kBT d by dr1 ln g of, and in fact, let's write it in this form, ln g of r1, r2, if you're thinking about not a spherical symmetric system. And if you're thinking about a spherical symmetric system, then you don't even have to talk about d of r1, r2, you can just talk about d of r. And in this context, we introduced something which was g was the same as e to the power minus beta w, or w is equal to minus 1 over beta ln g. So if you look at this equation now, this means that d by dr1 of u, or let's just talk about spherically symmetric things. So d by dr of urn is equal to kbt d by dr of this thing, right? So kbt multiplied by 1 over beta is going to cancel. So kbt multiplied by beta is going to, in the denominator, is going to cancel. And we have a minus sign here. So this is going to be minus d by dr1 dr of w of r. And this is why it's not g of r. G of r is the radial distribution function, but w of r is called potential of mean force, because, and notice this is a subtle equation. It's not really exactly obvious. In principle, you should be thinking of minus w of r as the potential of mean force if you're to be exact. But see what we have done here. W of, when in the right hand side, when we talk about W of R over here, we we don't have any averaging, right? It is just some W of R, some simple mathematical function, and we differentiate with respect to R, and we get a force that we would have calculated by averaging over complicated things, averaging over all n minus 2 particles, all except the 2 particles that we are interested in. So the average on the left hand side is hard to calculate, hard to perform, but the right side you could get out of experiment. If you know G, you know W, and if you differentiate it, you get the force experienced by particles. So that's why it's useful. So this is just to brush your memory. Now we will start from here and talk about, let's just go to the next page, talk about more thermodynamic properties from G of R. And in order to proceed further, we will become a bit specific. So we are going to start by talking about this U of Rn. This is the whole quantity, right? This is the things that making life very, very complicated. If this capital U of Rn, what is capital U of Rn? Capital U of Rn is really a function of R1, R2, R3, and all n particles that you have. Each of them has 3 coordinates. So it's a really 3n dimensional function. It's complicated. If you had ideal gas, it would be just a flat number and nothing would matter. We wouldn't have to do any of this. And in your homework, as well as at different points during this class, we have seen how things reduce to normal behavior for ideal gas. Remember, right time we drew the G of R for an ideal gas and we saw how it makes sense and things like that. This is quite generic. This is quite complicated. Here you could have particles talking to each other through their distance. You could have particles talking to each other as a function of their angle. You could have particles talking to each other as a function of some torsion. You could even, so this would be a 2-body interaction. This would be a 3-body interaction. This would be a 4-body interaction. And why stop at 4-body? We could go on to further. We could go on to complete n-body interactions, right? In general, everything talks to everything at the same time, right? However, what we are going to do is to simplify our life and focus only on, we will focus on pairwise additive interactions. So we are going to assume that we have only 2-body interactions. This doesn't mean that, so let's imagine I see Kishler and Shams right now on my screen. This doesn't mean that I don't talk to Shams or I don't talk to Kishler or Kishler does not talk to Shams. All in 3 of us, there are 3 possible pairs, right? All pairs contribute and our joint interaction is happening through as a sum of these pairs. In practice, we could have a term where all 3 of us talk at the same time. That's excluded. We focus only on 2-body. So how do we write this down? We will take the capital U, and this is where I hope my writing does not complicate things. And we will write it as a sum over different pairs, ij. So I and j could be 1 or 2. Small u, okay? This is a small u. How do you tell it's a small u? It's supposed to be smaller in size and it has a little tail on the back. Let's hope it's obvious from that. Mostly we will be using small u, so I don't think it'll be too bad, which depends on the distance between I and j. So we are down to our spherically symmetric approximation. Now, if we write it this way, ij equal to 1, ij equal to n, is this the right way to write this? Or should we be doing the summation a bit differently? Any ideas?
Shouldn't we omit double counting?
We should omit double counting. So how do we omit double counting?
Shouldn't it be some kind of combination like n choose 2?
Yeah, so the simplest way to do it is to just say I more than j equal to 1. Okay, this will take care of double counting. Otherwise you will be counting ij. Otherwise you will have 2 problems. You will be counting ij and you will also be counting ii, right? You don't have self energy. Particle does not really talk to each other, right? So this avoids both of them. If you wanted to include self energy, then you will put a more than equal to here, but we are not going to talk about that. Okay, so this takes care of double counting. So what does this small u of r look like? It only depends on the distance between two particles. So the small u of r is what we call a pair potential. It only depends on a pair of particles at the same time. And it will look like, and a typical example of u of r would be something like this, where if you bring two particles very, very close, u of r goes to infinity. It just blows up. And as you go down to r tends to infinity, as you go up to r tends to infinity, the interaction slowly goes to zero. And there is a well-defined minimum. This is a typical u of r. One way to model this is the Lennard-Jones potential, which is Lennard-Jones u of r is given as 4 epsilon sigma by r to the power 12 minus sigma by r to the power 6. And if you have done any quantum chemistry or quantum physics, especially quantum chemistry, you can kind of justify why does this have power 12 and power 6 over here. It comes due to van der Waals interactions and things like that. But if you plot this function for any value of epsilon and sigma, you will see that it takes this particular form. This is one example of a u of r. You could have also had a u of r for hard spheres, right? How would u of r look for a hard sphere? For a hard sphere, it would be infinity until the diameter of the sphere, and then it goes to zero, right? This is u of r for hard sphere. And this Lj, I just wrote the short form. It's actually Leonard / Jones. So this is a pair potential. We won't worry too much about the specific form of the pair potential today in class, although in your homework and in an exam, I can create some pair potential and ask you to work through the idea specifically using a pair potential, but the overall idea is going to just, the key point is that we will assume equation 1, that the full n body, capital N, so this is n body interaction, and this is sum of two body interactions, right? So this is a big assumption, right? It's like voters in an area deciding to vote whether Republican or Democrat, and you are saying that I can only talk to one neighbor at the same time, but it doesn't really happen that way, right? You have a big community gathering and everyone gets excited about something, blah blah blah. So we are saying no, all interactions will happen pair at a time. It doesn't mean the system cannot. It doesn't mean that you cannot talk with someone who lives very, very far from you. You talk to your neighbor talks to his neighbor, blah, blah, blah. And you might even have a direct interaction term with someone who lives very far off from you. But everything is just two body. So that's the idea. Okay. So one aside I want to mention here, which I posted on Slack, is there is something called Henderson's theorem, which says that if you know G of R, and if you assume pair potential, okay, you have to assume pair potential, then G of R leads to U of R uniquely. That's quite a powerful theorem. The proof is quite simple. If you go and read it, I put up a one-page proof on the Slack. I recommend you to read it. And in practice, it's another story. In principle, if you know the G of R, there is a unique pair potential that must have led to the G of R. And I recommend that you go and read it. You might enjoy it. If this is not a part of the, I won't be quizzing you on it really, but it's just related. So now, what do we want to do? What we want to do now is to calculate the total average energy of the system. With this preamble talking about pair potentials, we want to calculate total average energy of the system in terms of G of R, rho of R1, R2, and things like that. How do we do that? So total energy of the system will come from average kinetic energy, which depends on momentum, plus average potential energy. And this is capital U, right? Because it is the full energy. So far, I haven't made any assumption about whether it is, in this equation, equation 2, I haven't assumed whether it's pair interaction or not. It is just some generic equation. The kinetic energy we already solved for separately, and we know that is going to be 3/2 n kBt, right? We can just use equipartition. You did it in the homework, you did it in class, so this we have done multiple times. And then we need to figure out what will this thing be? And that's our challenge for now. How do we do that? I'm going to just write down the answer or ask you to help me write down the answer before I get into the proof, because the answer is actually quite intuitive. So what do I mean by answer? So I want you to tell me about so I want you to assume pair potentials, okay? I want you to assume that, okay, U of Rn is indeed made up of I more than j equal to 1, capital N, small u of Ri minus Rj. If this is the case, and your hint is, I want you to think about the reduced density distribution function rho of 2 R1, R2. Given these two informations, that the energy can be written as a sum of small u, and that you have access to rho 2, which is the reduced density function, could you have written down the value of this complicated average? Any idea? How would this look like? If you don't, if you get this right, I will definitely be very inclined to give you full participation points, even if you participate in this exercise. It's hard, but try to think. How should we go about doing this? And I will give you progressive hints if you get stuck. Go
Can
ahead.
you split up the potential into its like additive terms and then take the expected value of each of them?
Well, we already have additive terms, right? It just depends on u. We are adding over u.
Okay, so it would be the sum of the average of small u.
So, okay, you mind if I write an integral?
Okay.
So let me help
Cool.
you a bit more, Nathan. Let me write this down and then ask you to tell me, what is this missing? Is this correct, or is this missing something?
You need a sum on the outside from I greater than j to n.
Okay, let's say I'm talking about per pair. Okay, let's say I'm talking about, I will just put something which is proportional to. So we know how many pairs do we have, right? So, okay, you're right about the sum, but what I want, notice that this u is not separate for different pairs, right? U is same for 1, 2, 1, 3, 3, 4, 88, 89. So we don't really need to sum over ij. We can just write it down for 1, 2.
Okay.
In that case, what would we do next? And this is purely intuition based. I don't want to do any algebra.
Then you'd multiply by p of r1, r2 inside the integral.
P of R1. Actually, let's simplify it even more, and let's talk about spherically symmetric. Okay? Spherically symmetric. Or should we go into spherically? So no, let's not go to that. Okay, that's fine. What did you say? What should I multiply by?
P of r1, comma r2.
P or rho?
Uh,
It will be rho, because I don't care about the identity. Any two particles will do. Okay?
okay.
It will be not, you're almost there. Very good. So it will be rho. Is this correct, or did I still miss something?
We should be having a D row, right?
D what?
D row. Like we have the density, but
The
no, that
density
should
will play a role, because the density comes when we later approximate this to be rho 2 G2 R1 R2. But remember that rho square has the density inside it. The only thing that is missing now is a half. Again, we have double. Okay, so hopefully this equation makes some intuitive sense to you. you get the idea. Nathan was absolutely on the right track when he said the probability needs to be there, right? So you're saying, well, I will go to, and the n is already accounted for here due to the volume. And once we go to the proof, you will see why we don't have to multiply by any n or number of pairs or things like that. So this is what we are going to try to prove now. This is the result. Okay, this is the average energy. And if you further assume spherically symmetric thing, then it turns out to be even simpler. And then you can use what Kishler mentioned and put in the density and get down to G of R. But let's try to prove this, okay? So the proof for this will be that we go to our capital U of Rn and we use equation 1, okay? Use equation 1. What will that be? Equation 1 says that this is average value of summation I more than j equal to 1, capital N, small u of Ri minus Rj, this average, right? Now, if we are assuming that every pair has the same u, then instead of doing it for every I comma j pair, we can just do it for one pair. How many such pairs do we have? N multiplied by n minus 1 divided by 2, right? N choose 2 pairs are there. And now we have to average not over a sum, but we have to just average over any one u as a function of R12. And there is nothing phenomenal happening here. So if, for example, if you had a system made up of carbon and oxygen atoms, and the interaction between carbon-oxygen is different from the interaction between oxygen-oxygen and carbon-carbon. In that case, you won't just have one U, the particle identity will also matter. But if you're thinking about just monoatomic system, then it does not matter, right? And we can write it this way. So once we have this, so this is number of separate pairs. We can go further from here, and now we will derive equation number 3 rigorously. So in order to do this, we can write it down as n minus 1 by 2, and actually write down the average of this u of R12. What does the average of u of R12 mean? That means you go to all particles. The average always involves all particles. So in the numerator and the denominator, you will have d of R superscript n. The superscript n means R subscript 1, R subscript 2, R subscript 3, everything is accounted for. In the numerator, however, you will also have a R12 multiplied by exp of minus beta capital U. Remember, this is capital U. We are talking about the interaction energy of the full system. That's the definition of the canonical ensemble. In the denominator, you will simply have exp minus beta capital U Rn. Okay, this is the value of UR12. So now what we can do is to keep the half out and leave the denominator as dr capital N e to the power minus beta u of Rn. And in the numerator, let's look at this one. So what is this? This is integral dr1, integral dr2, integral dr3. But let's separate it out. Let's keep the R1, R2 part first. U of R12. So again, I want to emphasize this is small u, while this is, I should put a tail in my, normally it's clear from the quantity that you have inside the function. That's why we never write it without what is it a function of. If it is a function of R12, that's obvious, it's small u, otherwise it's not, but it can still be confusing. While these are capital U or n particle. So it's a sum of all two body terms. So with that, so what we have, we take this integral and we write it as dr1 r2, and we keep the u r12 term and bring it here. And we bring inside this n minus 1. Okay, and you will see why we do that, n minus 1. And then we do the everything else integral, drn minus 2 e to the power minus beta u of Rn. Okay, so this looks complicated, but in a moment you will see actually it's not that complicated and it simplifies into something simpler. Let me write it down again, what we just did. We have just said that n minus 1 by 2 average value of small u R12 is the same as half. In the denominator we do nothing. In the denominator we have drn e to the power minus beta u of Rn, and in the numerator we have separated the integral as a dr1 dr2 small u of R12 multiplied by n minus 1, then an integral drn minus 2 e to the power minus beta capital U of Rn. Okay, now I want you to recall that we defined rho 2 of R1 R2 as n factorial by n minus 2 factorial. Remember, we did not divide by 2. This was the definition. P2 of R1 R2, right? Or n minus 1. What is P2? P2 is integrate out everything else except R1 and R2. And in the denominator, have the full partition function. This was the definition which we started our study of classical fluids in Chandler chapter 7. So let's call this as equation number 4. So now notice that over here, the denominator is the same as what you had over here. And the numerator also is the same as you had over here. So our life is suddenly aha moment. Things simplified. This is nothing but half integral dr1 integral dr2 u of R12 multiplied by rho 2 of R1 comma R2, which is exactly what we wrote. With a bit of hand holding, you were all able to just write it down, right? It's the same idea, and you were just able to derive this, which is equation 3. So we were able to derive it. In this derivation, these type of derivations will keep coming in StatMech again and again and again, and you will stumble. Why will you stumble? Because I'm teaching the class, you are the one taking it. It takes time to learn there. You know, I took StatMech a little bit during my undergrad, then during my grad school, then I cleared it, and then finally something hit, like, oh yeah, now it makes sense. Then I taught it. This is the 4th time I'm teaching, and every time I teach it, I'm like, oh yeah, now it hits better, it gets better. So it's a progress. Some of you will be very lucky, it will hit just the first time. Otherwise, it takes time to go through these things. And all of these are subtle manipulations, like why did I write function of all n particles over here? Just think. And if you have even an iota of doubt, I love nothing more than getting your questions on Slack. Some of you ask on general channel, some of you ask on direct. Please ask me questions, specifically on channel, because others also might have that doubt, and no one is judging you. The more you ask, the higher your grades will be. Let's just put it this way. I don't care for anything as much as I care for, well, I care for your performance, but participation is also a big thing. So please ask questions. If it's clear, then it's great. But if anything is even tiny bit of doubt, then please ask. So we just derived equation 3. Now let's think about spherically symmetric molecules, where equation 3 can become even simpler. And there we can talk about density. Rho 2 of R1 comma R2 is equal to rho square of G R12, right? So now we can write down our capital U of Rn average as half. So I'm just writing this equation over here, okay? So half integral dr1, but I'm talking about spherically symmetric molecules. So I can, instead of integrating R2, I will integrate dr12, right? Which is the difference between R2 and R1, just a change of variables. And why did I do that? Because I know that the pair potential depends on R12 multiplied by rho square G R12, okay? What is half dr1? Notice that none of this has dependence on R1. This is dependent on R1 too. This is like in the reference, frame of reference of R1. What is the value of half integral dr1? Any ideas?
I just have a question for here.
Go
So
ahead.
for this R12, you write it as a scalar or the vector. Is there any difference? Because I see all the R12 seems to be not related to the directions, right?
Yeah, when I don't use a vector, it means this. Okay, it will simplify further in a moment. But Z, now that I have your attention, can you tell me what's the value of this thing in the circle?
Well, it seems like half of
Yeah. Go ahead.
half of a length, something like.
Half of a volume.
Sorry, volume?
Volume. This is half times volume.
Why? The volume should be integral over all of the directions, right?
R1 is a 3, R1 is R1X, R1Y, R1Z.
Oh, yeah.
Happy now?
Okay, so which means that your R1 is also, it is also a vector, right? You need to
Sure.
integral all of the
Sure.
R, theta, and phi.
Sure.
Okay.
But remember when we started, I already apologized that I'm not going to be writing this all the time, right?
Oh, okay.
Just my life too complicated and we'll never finish StatMech if we do that. And this is why, you might say that, oh, this professor is terrible. He writes everything from scratch. He does not come with PowerPoint lectures. But believe me or not, professors who teach from PowerPoint lectures can cover too much material without you knowing it. And I think I like teaching because I work with you on the fly. And if I make PowerPoint, I can cover so much more. We'll not learn. We'll learn even less. Okay, good. So this is half times volume. Let's go further. And now, since we have dr12, there is no point in writing R1 on R2. Let's just call it dr multiplied by u r, because we know, and so Z brought up an excellent point. So anytime I'm not, maybe I will write vector for this equation just to make it clear. R here is a scalar inside u of r, but before that it is a vector. So this one was a vector, this one is a scalar, okay? And this one is again a scalar. And well, it looks like a wonderful equation with, we can proceed further. Oh, we missed something, right? We introduced d over, so we need to have rho square that comes outside. So let's write this down as rho v by 2 d of r. Let's bring one row inside and let's write it rho g of r multiplied by u of r, okay? What is rho v? Rho v is n, the number of particles, right? So this is n by 2. And a row remains. So dr rho g of r u of r, and clearly this is a vector. We can switch to spherical coordinates now, and we don't care about the value of the phi and theta parts of the spherical coordinate. So this becomes n by 2 integral dr 4 pi r square g of r u of r. Okay, let's write it down on the next page clearly. So what we have said is that u of Rn for spherically symmetric molecules is equal to n rho by 2 integral dr 4 pi r square g of r u of r. And now we can write down the full thing, because remember, our main interest was in the total energy. Equation number 2 had total energy, kinetic energy plus potential energy. So we can write both of them. And let's call this as equation number 5. So use 5 in 2, and then we get our total energy is equal to 3n by 2 kBT plus n rho by 2 dr 4 pi r squared g of r u of r, and now everything is scalar. And if we want to talk about the per particle energy, this will be 3 by 2 kBt plus rho by 2 dr 4 pi r squared g of r u of r.
Can I ask a quick question
Go ahead.
on the last page?
Huh?
So just looking at the equations of 1 over 2 dr1 dr12 something like that. I think this is very similar to the Bernoulli equation or continuity equation.
Sure.
Is there any like connections of this equation with the fluid dynamics and stuff?
Well, this is why we are studying classical fluids, right?
Okay, yeah. I mean,
why the
are we
chapter
gonna?
Yeah, I mean, in
Yeah.
fact, as we go ahead, what is Bernoulli's equation? I think we'll talk about pressure, and that's exactly what we are going to do next. We are going to derive equation of state,
Okay.
which won't look like Bernoulli's theorem because there is a bit more dynamics there, right? So there is no dynamics here, but it will look kind of similar. For example, if you had an ideal gas, then we know U of R is 0, right? And
Yeah.
average E by N is equal to 3 by 2 kT. From this, you can show in one line of thermodynamics that pressure is equal to rho multiplied by kT, which is our ideal gas law. So it does that. But the wonderful thing here now is that you have terms that account for interaction between the system. If U of R is not 0, you can do more with this and derive equations of state which are more complicated. So we are going to look at two equations of state. The first one is actually, you are going to do it. It's Chandler 7.11. It's a bonus problem. It's 25 points extra bonus problem. So please do it. Okay, you might be able to find some solutions on the internet, this or that. I don't mind. Please work through it. Please try to, if you finish it, I will give you full points. But last time I gave bonus points, 4 or 5 of you attempted it. Others did not even touch it. I'm there saying like, please let me give you free points. And if you don't even try it, how can I give you free points, right? So please try Chandler 7.11 and I will walk you through the basic idea. Chandler 7.11 says is, so what is equation of state? Equation of state is really thinking about pressure by kT. One way of thinking about it in terms of rho. So for ideal gas, it will just be P by kT is equal to rho. But for non-ideal gas, we will have other terms that show up over here. So Chandler 7.11 uses P is equal to kT partial ln Q by partial volume at n comma constant n comma t, and it works through this. It assumes a cubic box. You will have to work through a bit of algebra. And here you can write down your Q only as a function of positions. So x1, x2, x3, y1, y2, y3. Actually, I shouldn't use x1, x2, x3 to confuse you. Q should be only a function of positions because the momentum part, we already know how it shows up in the formula for total energy. And you just work through all of this. It's just a few lines of algebra. It's not trivial. The algebra is a bit hard, but once you write down your Q, you will get an equation that looks like, and this is your hint for the middle of the problem, you will get to an equation that looks like partial ln Q by partial V at constant n comma t is equal to n by V minus 1 by 6V kT integral over volume of R12 du R12 by dr12 rho square dr1 dr2, something like this. This is your hint for this problem. So I'm going to work through a full derivation for another way of getting equation of state. This one I didn't want to do it in class and I want you to think through it. It's a bonus problem, but please work through it. And once you use this, you will get a final equation that looks like P by kT is equal to rho minus beta rho square by 6 integral dr g of r du of r dr. So you can express the deviation from ideality in an equation of state in terms of the g of r and in terms of u of r. So here's a semi-philosophical question. Why can't you express it only in terms of small u of r? Small u of r governs the interaction, right? When you have a non-ideal system, the only thing that is different from 0 is small u of r, right? So why is it that I'm writing a separate g of r here? Why is it that I cannot write this equation only in terms of u of r? Any idea? Anyone wants to make a guess?
Isn't G of R like uniquely determined by U of R? From the proof thing?
Correct. No, so the Henderson's theorem says opposite. U of r is uniquely determined from G of r. What I'm saying is, if you have U of r, why do I need to have a G of r here? Why can't I have a simpler equation where I write everything in terms of only U of r? Because U of r tells me everything about non-ideality, right? U of r is the interaction that's different from G of r. So the answer is entropy. This G of r helps us deal with entropy. If you think about in statistical mechanics, the partition function is indeed always given by e to the power minus beta e nu, right? So the energy of the system is, of course, completely determined by energy. The partition function of the system is always completely determined by the energy itself. But entropy is a subtle thing. Entropy boils down to being clever about calculating this nu and doing all this business. So this G of R in a way accounts for the entropy. In principle, yes, you could write down, if you're a mathematician, you could write down an equation here that has an integral inside an integral inside an integral, and it will look like everything can be done from U of R. True, but in practice, you will have to deal with entropy. And G of R is really your shortcut of dealing with entropy. It accounts for all possible arrangements, right? Remember when we did G of R, the idea was averaging over possible arrangements of everything else in the system except these two particles. That is entropy, the number of ways of arranging the system. And G of R simplifies our life. So in principle, you can get it only from U of R. In practice, to get the entropy, you will have to do a bit of work, and it's not going to be that simple, okay? So this is Chandler 7.11. This is one way of deriving the equation of state. This is purely mathy. I want to do something else, which I like a bit more. Notice the other thing here. This approach,
Question, Rick.
just let me finish one thing. This equation gives you P by KT is equal to rho, and then a second term, which is proportional to rho square, right? So yeah, I will come back to your question. Just give me one moment. So in general, the equation of state looks something like P by KT is equal to rho plus some term multiplied by rho square plus some term multiplied by rho cube. And in fact, you could keep going further, right? And as the density becomes smaller and smaller, you approach the ideal gas limit. As rho tends to 0, ideal gas limit is approached or reached, and P by KT tends to become rho. And these coefficients have a name. Typically, these coefficients are denoted as B2, and they depend only on temperature. Typically, B3 of T multiplied by rho cube. So this 2 indicates the power of density that you have. And these things are called second virial coefficient, third virial coefficient, and you can keep doing more and more. But the Chandler 7.11 approach lets you calculate the second virial coefficient. So here calculating the value of second virial coefficient using this approach. It does not allow you to go further. Yeah, what was the question?
My question is, how, so here we are considering the fluctuations as well on the particles. But how is that reduced to the Bernoulli's equation? Does it come to in the low density limit or in the low
I
temperature
don't know.
limit?
I'm not
or-
talking about Bernoulli's equation here, right? So this is something we should talk after class. So I'm not claiming if Bernoulli's
Okay.
equation will happen directly out of it. I will have to think more. However, I am telling you that
Okay.
equations of state can happen. So what you're asking is how do you get from equations of state to Bernoulli equation, right?
Yeah, exactly.
That's something I will have to read up on. It's not at the top of my head. Maybe Reeves' book talks about it, but I don't remember. So this I don't know. But what we are focusing on is equation of state. And equation of state is an equation connecting N, V, T, and pressure with each other, right? That's what we are talking. Because thermodynamics, we know that of all these, this is like the most fundamental point in thermodynamics, that you can characterize the state of a system by using all four variables. But at equilibrium, there is a constraint on the system. And that constraint means that any one of these variables can be written as a function of three other variables. You can write P as a function of NVT, you can write volume as a function of NT, P, so on and so forth. And any such equation is called an equation of state. And that's something, it's the ideal gas law is one equation of state, which you can derive using kinetic model, this or that for particles that are ideal. But what if it's not ideal gas law? What if there are non-ideal interactions? In that case, we have an equation of state which looks complicated and where the terms are there corresponding to higher powers of density, and those terms at the same time are all, if you really wanted to think about B2 is a functional of U of R and temperature. These two things uniquely determine B2. However, in practice, it becomes more useful to write it as functional of G of R, comma, U of R, comma, temperature. This doesn't mean that, as the Henderson theorem tells us, they are unique. G of R and U of R are uniquely known to each other, which is just like saying that if you know the interaction energy of a system, you can write down the partition function and you can calculate the entropy. But in practice, writing down the entropy separately has its own benefit. And that's what we have over here. So, and I'm going to read up on this. Maybe can you send me a message on Slack just so I can remember to read up on this, on the connection between this and Bernoulli equation?
Sure. Yeah, actually, like the fundamental question is say I'm suppose I'm a mathematician. I'm simulating some fluid, just as I remember one of our classmates were doing some research on that. Say I can use Navier-Stokes equation to simulate the fluids, or I can use the Bernoulli's equation to simulate some fluids, or I can use the approach we are using to simulate some fluids. Say by writing down their equation of states, then how are they connected? So that's
the most important thing you
that's
have to keep in mind is we are doing equilibrium statistical mechanics, which is in a principle quite boring because everything is equilibrium. So when you talk about fluids, the reason my ears go popping is because fluids are typically non-equilibrium. Navier-Stokes, it's so different because it's non-equilibrium, and things get
yeah.
complicated there, right?
Yeah, so that's why I mentioned the Bernoulli's
So
equation.
that might be that is so let's keep that for additional discussion before we proceed further, okay? Because this is equilibrium, and getting to non-equilibrium out of this
Sure.
is tricky because you're talking about transport.
Yeah, sure.
Right? And there is no transport here. There is no flux here. And we cannot really talk about Bernoulli and things like that if you don't have net flux. If you're talking about net flux, that's zero here. Okay, so, but that doesn't mean life is boring. Even without net flux, you can have, as you have been seeing this semester, there is a lot to learn. We were able to explain so many fundamental observations just from this picture. Okay, so
Yeah.
Yeah, go ahead.
Sure. Yeah, because I was wondering whether there's a simple equation like of writing down the kinetic energy or the potential energy
Any
in
such
terms of
approach,
dynamics.
any
yeah.
such approach will depend on linear response type of approach, which we are not doing right now. You have to talk about non-equilibrium behavior in order to do what you're saying. And the reason why I'm pushing you away is because we are still talking about equilibrium. Okay.
Yeah,
And
yeah.
it's exciting in
sure.
StatMech to jump into non-equilibrium. You know, it's especially as graduate students, you will find this tendency like, oh, I want to do active matter. There is a lot to discover and do even in so-called boring matter, which is equilibrium. There is a lot to be done. And that's what we are working on right now. But let me talk about the second approach, which is a second approach to equation of state, to EOS, equation of state, or virial coefficients. And this one I think is quite intuitive, and I like this a lot. Here, we are going to focus on our potential of mean force, W of R. Okay, and I'm going to stop in 10 minutes, but I'm going to start this. And it's so important that I want you to go and read up a little bit of it and then resume next time. So I want you to think about what is potential of mean force. So the potential of mean force is reversible work to move two particles from infinity to a separation R, right? And the reason why this is so hard to calculate is because when you're moving these two particles together, you are doing it not just in vacuum, but this is supposed to be an arrow. You're doing it in the presence of all these other particles that also exist. And anytime you move these two particles, everything else is going to respond, and you need to average over those configurations. But my question for you is, what would be W of R in vacuum? That is, what do I mean by vacuum? If only those two particles existed in the system, if only those two particles existed, or low density limit. So since Jingchen asked me so many questions, this is a question for Jingchen. Do you have any intuition here, Jingchen? What can I say about the potential of mean force if there were only two particles in vacuum? Your
Is it
hint
just D?
your hint is pair interactions.
Yeah. So like, is it like U R1 or D D
No,
U
you're
R1
right.
or 2?
It is just U of R. It is the potential energy.
Oh,
right?
yeah. So it's work, right? Oh, okay. I thought you were talking about the force. Yeah. Okay.
Yeah, no, I'm talking about the potential from which you would get the force. So in vacuum, this is important, you know. This is why I like this point. It starts from a very intuitive but important point. The W of R is equal to U of R if you had only in vacuum, if only those two particles existed. Now, in reality, that's not going to be true. So in reality, so if you had vacuum, in vacuum or very low density rho, in reality, that's not going to be true. We will have U of R plus some deviation from U of R. Well, let's call it delta W of R, right? We don't know what it is. This is going to be correction due to everything else in the system. So, and we can see now that the limit as rho tends to 0 of delta W of R must be 0, right? Because as the density tends to 0, W of R tends to small u of R, right? So the limit of, let's call this equation number, where are we? Lost count. Sometimes I just start arbitrary numbering, then students get confused as to where did the missing equations go. Let's call this equation 7. There might be another 7 behind, but that's okay. So now let's think about our G of R. What is G of R? Well, G of R was defined as e to the power minus beta W of R, right? So G of R is e to the power minus beta W of R. So this can be written as e to the power minus beta U of R plus delta W of R. Okay, that's how we defined it. So this is equal to e to the power minus beta u of r e to the power minus beta delta w of r. And we know that e to the power kx as x tends to 0 is 1 plus kx, right? Or order of x, right? We don't have to worry about the k, we just call it order of x. So we can take this equation and write it as e to the power minus beta u of r multiplied by, so this is exactly that thing, right? This delta w tends to 0 as rho tends to 0. So we can write it as 1 plus order of density. So g of r is equal to e to the power minus beta u of r 1 plus order of density. Now we showed, again, I'm not going to finish this derivation fully today. I'm going to set it up today and then we will work on it again next time, because this is, it can be done quickly, but I will be just rushing everything and I don't want to do that. We showed that the average energy per particle is equal to 3 by 2 kBT plus half rho d of r g of r u of r, right? So we can now define a deviation delta E is equal to E minus E ideal. What will be E ideal? E ideal would be just 3 by 2 kBT, right? So we can define a delta E this way, where delta E by N, or average energy minus E ideal, delta E by N would just be rho by 2 integral d of r g of r multiplied by u of r, right? But we know something about g of r now. We can write it as u of r multiplied by this thing. What is that thing now? So we write it down, e to the power minus beta u of r multiplied by 1 plus something, which is order of density. So this is going to be our main equation next time. We will use it to derive terms which allow us to get higher order terms in rho. This will lead us to other equations of state. We are going to use two thermodynamics. We will do this next class. We are going to use two thermorelations that you have to do in your homework 4. So I recommend doing it before the class, so you already have one problem done from your homework. It's got nothing to do with StatMech. The first one will be that delta E by N is equal to partial beta delta A by N divided by partial beta. And the second one is rho square partial beta delta A by N by partial rho is equal to beta P minus rho. These are purely thermodynamic, and I can give you a hint for this one. For this one, your starting point should be that partial A by partial beta, the Helmholtz free energy, is equal to S by KB beta square. You start from there, and you can do it in a couple of lines. And for this one, your hint should be to start with V is equal to rho V is equal to N. So V is equal to N by rho. So dV is equal to minus N by rho square, d rho dot dot dot. So try to do these two thermorelations. If you don't do it, that's okay. Just at least get familiar with the essence of these relations. And you will have to do it before you submit the next homework. We'll be using these two thermodynamic relations to finish our story and again derive equation that looks like beta P is equal to rho plus rho square B2T plus order of rho cube. And the key physical idea here is that the potential of mean force is equal to the potential energy in very, very low density. And we are thinking of an expansion where the higher density terms arise naturally. Okay, any questions about this? So as you can see, we are getting into slightly advanced territory. We have done all the basics. There's a lot of material that I'm throwing at you. If you keep reading through Chandler, it won't be too hard. Once we do this, we are going to get to something else, which is really fascinating. It's called statistical mechanics, perturbation theory. You have all done perturbation theory in quantum mechanics, but this will be the statistical mechanics equivalent of it. It's especially close to me because it was done by someone named Zwanzig, who was a professor in our department for many, many decades. And that theory is also quite useful and interesting, because what it does for you is to allow you to study a system with interacting potentials in terms of a system with slightly weaker potentials, which in turn can be simulated as a system with even weaker potentials. So you can set up a ladder. If you have a system with very complicated interactions, you can calculate its property by weakening the interactions a little bit. Well, why not go one step further, weaken it a bit more? And in the end, you can just go down to ideal gas. You will have a ladder of systems, and you can use this ladder to, in principle, calculate anything. And it's used in drug design, for example, heavily. I think there are companies which make millions, if not fractions of billions of dollars by using that equation, which was done by Zwanzig. So that's what's to come next. Once we finish Zwanzig's perturbation theory, then we will talk about phase transitions. We still won't be doing the really non-equilibrium, but that part is the fourth part of the semester where we did our introduction to StatMech, where we defined all the ensembles. That was the first part. The second part was looking at applications to non-interacting systems, even though, as I think Grishma pointed out, that calling fermions as non-interacting is a bit of cheating, but that's what it is. Then we went to classical fluids, where we had interactions. What do we mean by interactions? By interactions, we mean that U of R was not zero, and that's what we have been dealing with. And so this was the third part. The fourth part will be phase transitions and critical phenomena. So this is what comes next. Okay, if no more questions, I will see you Thursday.